Okay, guys, so here's H-31. All right, this is about the extreme value theorem. Okay, and I want to get a few things out of the way first. So note, if you see this, if you see C and then A is less than or equal to C is less than or equal to B, what that means, another way of saying that is that C is on the closed interval AB. All right. So if you see this, it means that, and vice versa. Okay. Now, if you see this, the only difference between what's up above and this is that it's not less than or equal to, it's less thans. That means that C is on the open interval AB. So it's not including the endpoints. Okay, guys, the extreme value theorem is often stated in different ways. Okay, but so here's a bunch of ways it can be stated. So if f is continuous on the closed interval AB, then f attains both an absolute max and an absolute min on that closed interval. Okay, so let me just show you a picture here. All right, let me show you three pictures that will describe the extreme value theorem. So if you have, here's a situation where we've got f is continuous on the closed interval AB. All right. Well then, guys, you've got f of A is the absolute max. Okay, that's the highest y value overall. And you've got f of C is the absolute min. That's if f is continuous on the closed interval. Now here's a situation where f is continuous on the open interval. And guys, the absolute max and min, they do not exist because, and we actually talked about this like the very first day of calc, but if you've got like an open interval, all right, think of this sequence of y values. Guys, I can always, even if I think I'm at the lowest y, because this is an open endpoint, even if I think I'm at the lowest y, I can get lower and I can keep getting lower. And anytime you think, oh, I'm at the lowest one, you can keep getting lower. Same thing for this potential max. You could just keep getting higher. As soon as you think, oh, I'm as high as I can go on this graph, you can go higher. All right, so it's important for the extreme value theorem that that f is continuous on the closed interval. Continuous on the open does not guarantee that you have an absolute max or min. You could, okay, you could, like it could be something like this, you know, and then you would have an absolute max, but you wouldn't be guaranteed. Right? It wouldn't be guaranteed unless the interval was closed. Right, now here's a situation where f is not continuous on the closed interval. So they need to give you a closed interval and they need to tell you it's continuous because look here, this function is not continuous and we've got this asymptote. So this keeps going up to positive infinity, this keeps going down to negative infinity, so we don't have a highest or a lowest number overall. Okay, now often the extreme value theorem could be stated like this. It could be stated like this, or it could be stated like this. If f is continuous on the closed interval AB, then there must exist values C and D on this closed interval for which f of C is less than or equal to f of x, which is less than or equal to f of D for all x values on AB. Okay, so x could be any x value on AB, and these numbers C and D represent the inputs for the very lowest y and the very highest y. So this is another way of stating that f attains both an absolute max and absolute min. All right. Sometimes the extreme value theorem is just going to tell you about a max or a min. So if f is continuous on AB, then there must exist a value C between A and B. It could be A and B because it's less than or equal to's, for which f of c is greater than or equal to f of x for all other x's that are also on that interval. Okay. And then this one is just, instead of the greater than or equal to for f of c, it's less than or equal to, but it's the same thing. So read those over, guys, by yourself and familiarize yourself with that and try to visualize, especially these three, what they are saying. Okay, the practice is on delta math. All right, so we're going to do 3 examples. Oh, yeah, okay. So I needed 4 examples actually. So selected values of the function f are shown in the table below. There is a number c in this closed interval such that f of c is greater than or equal to f of x for all x also in this interval. Determine the validity of the following statement. So f is continuous on the closed interval. So guys, the extreme value theorem says if f is continuous on AB, then, any one of these things, they're all basically saying the same thing in different ways, then any one of these things have to be true. So it says if this, then this. It does not say if this, then this. So it doesn't go backwards. It doesn't say if we've got an absolute max, then the function must be continuous. So here they're kind of trying to trick you. So the question is, the statement must be true, the statement must be false, or the statement could either be true or false. So guys, they're telling you here that f of c is greater than or equal to f of x for all other x's in this interval. So here they're saying f has an absolute max on 1/8. Guys, just because f has an absolute max on the interval does not necessarily mean that it's continuous. And I gave you actually, here I've got a little example. Here's a situation where f of c, okay, here's all the other f of x's. Here's all the other f of x's. This f of c is greater than or equal to all the other f of x's where x is between 1 and 8. But this is not continuous. All right, it's not continuous. So if they give you that you've got an absolute max or min, it does not imply that the function is continuous, but it could be. So the statement could either be true or false. Okay, next. Selected values of the function f, which is continuous on this closed interval, are shown in the table below. Determine the validity of the following statement. There is a number c in this closed interval such that f of c is greater than or equal to f of x for all other x's in that interval. Guys, this is the extreme value theorem. This is the EVT exactly. Okay, and the extreme value theorem says that if a function is continuous on the closed interval, then it must achieve an absolute max and an absolute min on that interval. All right, here they're just stating the absolute max, but it's the same thing. All right, so this must be true. This is what the extreme value theorem tells us, is that this must be true. Okay, 2 more. All right, so selected values of this function, which is continuous on the closed interval, are shown in the table below. Determine the validity of the following statement. The maximum value of f on the interval 0 to 3 is 10. All right. Guys, this actually, so I took these points and I plotted them. All right, now, since f is continuous on the closed interval, the extreme value theorem says that it must achieve an absolute max, a highest y, and an absolute min, a lowest y, on the closed interval, but it doesn't tell us what that y is, okay? So guys, these are just 3 points, but this is a continuous function. So you don't know, it could go like this. It could go like that, in which case the absolute max would be here. All right? If we knew that instead, like it went something like this, you know, then for sure that would be the absolute max for the pink scenario. But this orange scenario, you know, nothing tells us that it can't go like that. Or a continuous function can be very loopy. So this statement could either be true or false. Okay. The EVT, the extreme value theorem, only says that a max exists. It doesn't say what it is. Example 4. Selected values of this function are shown in the table below. The function f is differentiable, okay, meaning that it has a derivative, and has f prime of x less than 0 on this closed interval. Determine the validity of the following statement. The maximum value of f on -3, 0 is 1. All right, a couple things to say here, guys. Differentiable means continuous and smooth. So if a function is continuous, then it's not necessarily differentiable, because just because it's continuous doesn't mean it's smooth. But if a function is differentiable, it's got to be continuous, because differentiable means continuous and smooth. So differentiable on -3, 0 implies continuous on -3, 0. And that's the hypothesis, that's the condition for the extreme value theorem. All right, so they're telling you in a roundabout way that the function is continuous. All right, so right away, since the function is continuous, we know that it has an absolute max. Now, what are they telling us here? If f prime of x is less than 0, guys, f prime of x less than 0, what does that mean about f? It means f is decreasing. It means f is decreasing. So this is a different situation. Right up here, they didn't give me any information to tell me that I can't have the orange graph. But here, when they're telling me that f prime is less than 0, that means that f has got to just be decreasing. So guys, f continuous on -3, 0 means the EVT applies, meaning that there is an absolute max and an absolute min. And then this further information tells us that our graph can't go up any further. It's got to just keep going down. So here, the statement actually must be true. Alrighty, guys. So practice on delta math.